Hi, I'm Robert Crowe, and today we'll be diving into Flax NNX, a new neural network library for JAX that aims to simplify machine learning development. We'll explore its core concepts, compare it with PyTorch, and see how it fits into the broader JAX ecosystem. This is the first episode of a three-part series introducing Flax NNX. In this episode, we'll explain its core philosophy, how models are structured, and how state is managed. We'll focus on the what and why of NNX from a Python developer's perspective. So let's get started. Flax is a powerful neural network library built on top of JAX. It's designed to be flexible and performant, making it a great choice for research and production. Flax NNX is its newest iteration, building upon and improving the previous Linen API. Flax NNX was created to address some of the challenges of working with JAX and neural networks. It provides a more Python-friendly interface, explicit control over state management, and uses familiar object-oriented concepts. NNX's design centers around three key principles. First, it embraces a Pythonic interface. Second, it emphasizes explicit state management. And finally, it defines and utilizes a Python graph data structure. If you're coming from PyTorch, you'll find that NNX offers a relatively smooth transition to JAX. The API design and architectural patterns are similar. We'll look at some code comparisons in a few slides. First, let's dive into core concepts. The foundation of NNX is the NNX module. This is the base class you'll use to create your own layers and models. NNX modules own their own state, including the model parameters. This code shows how to use a module to create a layer with a random parameter. Notice the explicit use of RNGs, or random number generators, to generate the random values. This is a critical point and major advantage of NNX, especially in version 0.11 and after. NNX modules are not just Python objects, they are also fully fledged JAX PyTrees. This is the magic that bridges the two worlds. You get intuitive, object-oriented experience of Python with NNX, where you can mutate state and share layers just like in PyTorch, while also getting seamless native integration with JAX's powerful function transformations like jax.jit and jax.vmap. You no longer have to choose between an easy-to-use object model and powerful functional backend. NNX gives you both. Here's a simple example of an NNX module Python graph for a very simple linear model. Notice that the weights and biases are NNX params, while the dimensions are simple Python. By the way, notice that NNX.display, which is used here, makes displaying a Python graph in a notebook really easy, and it's very useful when you're debugging. Here's a more complex example showing nested modules, forming the layers of a model. NNX.display uses the treescope library, which allows you to explore Python graphs visually. Accessing these submodules or parameters later is also standard Python attribute access, model.layer1 or model.layer1.weight. And importantly, standard Python reference semantics work exactly as you'd expect. If you create a layer and assign it to two different attributes, maybe for weight sharing between an encoder and decoder, both attributes will point to the exact same layer object in memory. There's no hidden copying or unexpected behavior here. It works just like Python references always do. So structurally, defining your models in NNX can feel quite similar to PyTorch. Now, let's dive into how state, like the actual weights and biases, is managed within these objects. State management is explicit. Static configuration like hyperparameters, so dropout rates and hidden sizes, are just stored as regular Python attributes. The dynamic state, things that change or are learned like weights and parameters or batch norm statistics or buffers, are held within special container objects, primarily NNX.variable and its subclasses. So NNX param, for example. And these are trainable parameters. Think of NNX param as analogous to torch.nn parameter. You access the underlying JAX array using the .value attribute. Crucially, these NNX variable objects allow for mutability. If a layer needs to update its internal state during the forward pass like batch norm does, it can directly assign a new value to the .value attribute of its state variable. This is a key difference from the typical immutable style often used with JAX PyTrees. And as mentioned, reference sharing works exactly as you'd expect in Python. If you create a layer or a parameter value and assign it to multiple attributes or parts of your model, they all point to the very same object in memory. This is essential for patterns like weight sharing, and Python graphs handle it naturally. Here's an example which demonstrates reference sharing exactly as you'd expect in Python. NNX provides different types of variables to manage different aspects of your model state. NNX param is for learnable parameters, and NNX state is for mutable variables that change during the forward pass. This example demonstrates the use of both NNX param and standard Python containers. Weight is a learnable parameter, while bias is a Python dictionary that can be updated. JAX requires explicit handling of random numbers, and NNX provides the nnx.rngs object to manage this. This is crucial for reproducibility, but nnx.11 makes this even more robust. When you pass an RNGS object to a layer like NNX linear, the layer doesn't just hold a reference to the original, it creates its own unique forked copy of the RNG state. This might seem like a small detail, but it's a huge win for preventing subtle bugs. It means that two layers can't accidentally use in advance the same RNG stream, which makes building complex, vectorized, or scanned models much safer and more predictable. NNX uses eager parameter initialization. This means that when you create a module, its parameters are immediately initialized. You also need to provide all shape information up front. NNX also provides a functional API with split, merge, and update. These functions allow you to separate a module's architecture from its parameters, which enables interoperability with pure JAX transformations. This example demonstrates the functional API. We use nnx.split to separate the module structure and state, and nnx.merge to reconstruct it. The counter state, as you can see, is preserved. You can learn more about JAX and the entire JAX AI stack with these coding exercises, quick reference docs, and slides. To watch the whole Learning JAX series, check out our playlist on YouTube. There's a growing community on Discord for JAX, and here's an invite link, and here are links for the docs for JAX, Flax, and the JAX AI stack. So, we've covered the fundamental building blocks of Flax NNX. We've seen how NNX module and Python graphs provide an intuitive, object-oriented way to define our models, manage state, and even interact with JAX's functional world using the split and merge API. With Flax NNX, we can take these Pythonic modules and make them run on incredibly fast accelerators. Coming up in our next episode, we dive into the most critical performance tool in the JAX ecosystem, just-in-time compilation with nnx.jit. We'll explore what a pure function is and why it's key to unlocking the speedups of 1000x or more. We'll also demystify the difference between the standard JAX transformations and their powerful NNX counterparts. So, see you then.